Astronomers for Planet Earth is an organization of professional astronomers and educators dedicated to helping people understand the causes, consequences, and solutions for climate change. This webinar series brings in experts to share their work to help you, the listener, be better informed and able to make a difference. Our host is Dr. Travis Rector, an astrophysicist at the University of Alaska, Anchorage. Dr. Faustine Cantalloube is a researcher in instrumentation for astrophysics, applied to exoplanet imaging with ground-based telescopes working in the near-infrared. She currently works at the Max Planck Institute for Astronomy in Heidelberg, Germany. Being concerned with precarity among early career scientists, with an intent to prepare the future generation of instrumentalists to work together in globalized research, Dr. Cantalloube created the Network for Young Researchers in Instrumentation for Astrophysics in 2017. Outside of her work, Dr. Cantalloube does outreach activities to a broad audience as a means of increasing inclusion, diversity, and critical thinking, utilizing the public's fascination with astronomy to trigger discussions about societal issues. The climate crisis has been a major focus for Dr. Cantalloube, as it is the biggest challenge society is currently facing.
Hi everyone, my name is Travis Rector and I'm a professor of physics and astronomy at the University of Alaska, Anchorage. I'm also one of the organizers of a group called Astronomers for Planet Earth. It is an organization of professional astronomers, educators, and students who are interested in helping out to address the problem of climate change. And our speaker today is Faustine Cantalloube from the Heidelberg Institute, and she is going to be talking with us about the impacts of climate change in astronomy. Faustine, thank you for joining us today.
Thank you for inviting me. Hi everyone, with a bit of delay, of course. As astronomers, we do have different ways of communicating and raising awareness about climate change. And for instance, we could discuss about how unique our system is, the climate on other planets, or starting with the Drake equation, which gives a kind of probability of finding intelligent life, so to say, in the universe. But also, in order to really raise awareness among our own community, that's exactly what Astro4Earth initiative is about. We should also look at our impact on doing research activity, how it impacts the climate change. But here, what I'm going to talk about today is to take the opposite angle and look at how the climate change is already impacting astronomy. That is to say, the quality of the astronomical data that we have. So this work I've done with several people because I'm not a climatologist myself, I'm just a researcher. So I'm working with climatologists and meteorologists. So first of all, to give you a little bit of my background, so I'm working on exoplanet high contrast imaging, and this is the most sensitive imaging technique that we have today, which means that we're really sensitive to tiny effects of the atmospheric turbulence, so the Earth's atmosphere. And so within that topic domain, what I'm mainly doing is the image diagnostics. So I'm taking the state-of-the-art instruments and trying to understand what are all the residuals, the optical aberration that we have. And with that knowledge, I'm really developing image processing techniques to try to find the exoplanets, or for instance here, the first protoplanet candidate here in this image around the star PDS-70. And I'm developing techniques to also see the disk and trying to analyze those data. And I'm using all of that knowledge to try to prepare, and hopefully I'm not only trying, but to prepare the extremely large telescope, the future ELT-39 meter telescope that will come soon on sky, 2026, hopefully. So that's really what I'm doing mainly. So of course, if you have any questions, comments, or suggestions about all of the work I'm going to present after, you're more than welcome to write me on this address. I'm very open to criticism. And sorry for my French accent today. So the rationale behind what we are doing today is that we just figured out that observatories are amazing because they've been collecting so many data about the environment. So we have more than about 30 years of data collected, and it's completely suitable for climate studies. So we can't study anything less than 30 years if you want to see climate trends. I'm going to come back on that. So the idea of this was to take all of those data and compare them to reanalysis data, to models that are fed with new measurements and rerun with finer grids and more information about the physical processes at stake. The second thing was, of course, to see the impact on astronomical data. And the last point was to project to the next century in terms of like how it's going to be at the ELT era, for instance. So we started very recently that study, actually in January 2020, and we are only now in September. So as I said, I had to learn things like pretty quickly, and I really worked with climatologists and meteorologists and atmosphere scientists who are experts in that field, so that I didn't misinterpret all of the things I'm going to show you. So one very simple aspect, so we're observing through atmosphere. And so why do we use ground-based instruments? So there are several reasons, but first, because we can build bigger telescopes, so we can increase the sensitivity and also the angular resolution we can reach. We can put a very stable, very big instrument that we can't send to space because they're too big, too heavy. And having a ground-based telescope makes it very stable. We can easily fix and upgrade instruments. We can also like try new instrumental concepts, which we can't do with space observations. And also the timeline is clearly not the same. So that's explaining just why we just don't go to space. So with that framework, we really need to study atmosphere, because of course we want to design the instruments through simulation, check robustness and everything. Second, the calibration, how do we, for instance, remove the telluric lines, so the atmospheric lines. We want to diagnose the instrument, understand how each element is working and what does it bring, what are the residuals after, and also assess the performance, which is the interaction between all of the subparts of the instruments, what are the final performance of an instrument. And of course, we also want to optimize the observation scheduling. That's something quite important, and it's going to be even more important at the ELT because one night on one instrument is quite expensive, as you can see here. So this study we made at the for the Parallel Observatory in Chile. Why? Because it's been started in '98, and then first light was in 2004, if I remember correctly. I mean, so it's located here in Chile, as you can see. So it's in the Atacama Desert at an altitude of 2,635 meters. This is a very specific site. It's one of the driest places on Earth. So on this image here, you have the temperature. So it was just at 1 p.m. today, 1 p.m. Local time today. So it was 13.5 degrees at the location of Parnell. So of course it's winter at the moment. And you can see this green line. I don't know if you see my, you see my mass here, which is the Andes, which are higher, so colder. So it's a very specific place, as I said, mainly because it's the driest place on Earth, and you have this very specific thing. So here is the Parallel Observatory with the 4 unit telescopes of 8.2 meters each. And you see here the Pacific Ocean, and all of the clouds, they're really stopped by the Andes, by the mountains. So that makes a very, the interface between the ocean and the ground is the continents. Is something very specific and quite difficult to model. And just to let you know, so this is here, if you see what Parnell's location. So we see again the first ridge of the Andes, then there is a kind of plain, and then there is another second ridge with a very high mountain. And here is the Cerro Amazonas, where they are building at the moment the extremely large telescope foundation, as you can see here. So this site is slightly higher, and again, the climate might be, the weather might be quite a little bit different, because you have this region is slightly, and it's completely, it's like 20 kilometers eastward of Parnell. So just a few things before we deep dive into the details. So climatology is really studying the long-term trends. So as I said before, it must be above 30 years, because what you're looking for is that everything that goes beyond the natural trends. So for instance, at Parnell, you have heard about El Nino and La Nina events, which are 2 to 7 years periodic trends in temperature. You also have something called the Pacifical Decadal Oscillation, and as the name says, it's about a 10-year trend. So if you really want to see something above the noise, which are the natural trends, then it must be above 30 years. So climatology really deals with this very large spatial scale. So that's the last column. So it's what is called the synoptic scales. So it's very big, like the current, I've lost the word, but the current exchanges on the globe. Atmosphere science is more dealing with between the present and the future. So it's more the mesoscale, so a few 100 kilometers. And turbulence is, on the contrary, something completely instantaneous, and it is very, very small, so small that the only way to describe it is to have a probabilistic description. So maybe you've heard about, for instance, the representation, the von Karman representation of atmospheric turbulence or this thing. That's the only way we can describe it. And so this is very small spatial scale and very local. So the link between all of those things, those three scales, that is temporal or spatial, is quite difficult to assess, actually. It's not straightforward. So we know the physics of what makes the turbulence, but we don't know from the turbulence to the global scales what exactly is the thing. And so that's why we thought that this study was quite interesting, because maybe astronomy, we do have some data, and we see in our images some details that could be maybe useful to better understand the links between all of those scales. So here on this image, you have, for instance, I will come back on that, you have, for instance, a humidity sensor. Oops, again. So just one word about meteorology. So it's a subtopic of atmospheric science, and it's really about forecasting and prevision. And aerology, again, sorry for my accent, as a subtopic of atmospheric science for free atmosphere. So free atmosphere is when it's about like 200 kilometers high, and it's when you're not anymore disturbed by the surface interface. So again, I'm not an expert in those fields, and I really had like helps from specialists and experts to make sure that what I'm saying is not wrong. So hopefully everything I say should be good. So now I'm going to start by giving you 4 examples of climate change impacts. So again, I'm really focusing on Cerro Parana Observatory in Chile. So first, the first thing you would think about under like anthropogenic global warming is, of course, the temperature. So we took data from 1998, as I said, when they chose the site, the Cerro Parana site, to today. And what we can see here in those data is quite obvious and obvious. It's still like more than 30 years, is that you have a huge rise in temperature in 2015. So we go from an average of 30 degrees, so this is a yearly median, the plot that I'm showing you here, to almost 50 degrees here, which is more than what is expected. So today, we think that the global average temperature increased by 1 degree plus or minus 0.2. And here we have 1.5 degrees. So that's the first thing. And we wanted to check that with, as I said, models. So those models, there are models run with all of the measurements we have on Earth. They put it in a huge box and they put the best they know about the physics. And so it's called the reanalysis models. So that's those things. So we use the European one. So this is the European Center for Medium Range Weather Forecast, the ECMWF. We could do the same with the Japanese model or the American model, for instance, and that's something that we would like to do. And so the one we use, the model we use is the ERA 5. So ERA 5 spans from 1980 to 2020. And it's quite interesting. It's probably the best to use in our case because it has a spatial resolution of 31 kilometers. So 1 pixel is 31 kilometers. And we interpolated it, in Parana, at Parana Observatory. One thing I also wanted to know now, a parenthesis, is that the Southern Hemisphere has very, very few measurements for 2 main reasons. First, of course, the Southern Hemisphere has less land. So we have South America and Australia, and that's the big, and a part of Africa. But also all of those countries, they're in a social economic background, which is not as high as the westernized country. So they have less institutes to study it, but they also have less airports. And airports are huge, how do you say, sorry. So airports have a huge amount of data collected every day. So the more we have data, the better those reanalysis data are. So we have very few data in the Southern Hemisphere, and that's something that also, again, Astronomer could help because we have many observatories in the Southern Hemisphere. And the other thing I wanted to say about that is that satellites are too recent. It's usually 10 years. And as I said, again, if you're below 30 years, you can't say anything about climate. So if we compare here our data from Parallel in red, bottom, and the blue one, which is the ERA 5 reanalysis data, you can see that the trend is matching. there is an offset because the altitude is not exactly the same. So it's 2000 for the blue line and our data are 2600. But the trend is there, and we see again this 2015 thing where it really suddenly rises above the natural trend. And another one, we took a longer time span. So we used this time the reanalysis era 20C, those spanning from 1900 to 2010. So it was the 20th century reanalysis data. The problem with that is that it's slightly bigger. So 1 pixel is 130 kilometers. And we also interpolated at parallel, but it's really bad because the pixels that we have are really in between the famous ridge I told you, so Pacific, and then the coastal range, and then the ridge. So we don't really want to interpolate really the thing, because we really erase the orography, so the mountainous range, and also the interface between the Pacific Ocean and the coast. So, but still it gives a trend, and we see the same trend on the longer time span. So we see that it's roughly flat, and then the 80s come and it's increasing, and then it stops. But so we already see actually an increase before the one that we saw at Parnell Observatory. Let's see, and maybe we can see, here. And maybe you can see a little bit better. So this time it's only the ERA 5 data that I told you about before, and we did a rolling average. So the blue one is the monthly average curve. So you see the summer on up and the winter down, obvious. So every 6 months, so you have this 6 month trend. And on top of that, we did the orange curve, the 1 year rolling average here. And you can see typically El Nino and La Nina effect. So you see those 4 years trend up and down. But what you can still see, here I'm moving the thing, is that in 2015, again, we really see that the temperature is rising way above this natural trend due to El Nino, La Nina, and even above the Pacific decadal oscillation, which is about 10 years. So this 2015 moment is called the time of emergence. That's the moment where the signal appears very clear above the noise, or not the noise, but the natural trend. Sorry, my astronomical background is coming back with the noise. So that's something. So now what is the effect on the atmospheric, the astronomical data? So as you might know, every dome during the day is cooled down so that at the opening of the dome, which happens usually at sunset, the external temperature and the internal temperature inside the dome is the same. If it's not the same, if the dome is warmer or cooler, then you have heat exchange, and it creates turbulence because the air is a very bad thermal conductor, which means that cold air and warm air does not mix really well, and it takes some time. So the idea to avoid that, a maximum, is to really cool down. So when you enter a building, one of those domes during the day, it's way cooler than in the outside. And by design, this heating and ventilation air conditioning system cannot be set at a temperature above 16 degrees. That's it. That's just the technique. It could be changed, but today that's how it works. And what we noticed is that there are many, many days where actually the sunset temperature, the real one, which is shown on the right plot in green, is above this red line, this 16 degrees. And so at those moments when it's above here, we have to set the system at 16 degrees. But you're gonna have this internal turbulence, what is creating the so-called dome seeing. And the dome seeing is creating, some internal turbulence, so it's degrading the resolution of your instrument. And what we noticed as well, so we looked at the occurrence of the sunset temperature being above 16 degrees with time, since 2006 in that case. And we noticed that it's increasing. So it goes along with what we observed with the temperature sensors. So every year the occurrence is higher to be in that situation. So for the ELT, we need to just keep that in mind, and also to upgrade maybe this system. So now what we did for the ELT, we have to keep that in mind. So we try to find a projection. So maybe there is the CEMIP initiative. So it's a intercomparison model, and every 2-3 years with the IPCC, they launch, many institutes can register and say, they give the input and the output, so what they want as an output, and they say the initial conditions. They give several scenarios. So the scenario where we stop every CO2 emission, for instance, or the worst case scenario, which is we just carry on the emitting at the same rate that we're emitting today, and so on. So they have different scenarios, which is usually called SSP5, and the very latest one, the SEMIP6, which is actually due this year for the next IPCC. So it's very recent, and all of the institutes registered didn't give their inputs yet, but it's completely available online. So all of those data, the ERA5, ERA20C, and those SEMIP projection, you can find them online. And so we used one of the model. So it's usually what we call model ensemble. So we used the Beijing Climate Center for this specific case, because we had it and we thought for different reasons that it could be the best for our case. And we used the worst case scenario, so which is called the SSP5 8.5. And we matched it with, because usually it's given in anomalies. So in climatology, everything more or less is given in anomalies. So anomalies is just plus or minus the median at the pre-industrial era. Okay, so if the temperature was 13 degrees at the pre-industrial era, is like how much you plus or minus this value. So that's what you can see here. So the green curve is the ERA20C, the 20th century reanalysis data. And the orange here, the big one, is the projection. So if nothing is changed, so you can see indeed that in the 80s it goes up, that in 2015 it really rises. No, we can't see that, but it's here, sorry. But so if it carries on like this, we will increase the temperature at the parallel location by about 4 degrees in 80 years. So that's really something that we also have to think about when we're designing the instruments and the cryostats of the next generation of instruments and telescopes. Okay, so now the second example that I wanted to give you is the surface layer seeing. So we noticed that the seeing measured by a dim monitor so from 98 to 2016, that's the blue curve. And then the 2016 one was slightly, was clearly increasing, but several things happened. So in around 92, the parallel mountain was flattened or leveled to put the telescopes. And then one by one, the UTs, the unit telescopes, were built. So it's kind of changing the airflow. And then the VLT survey telescope was built as well. So it's completely changing the airflow. And the dim was first on a tower quite high, and then we put it lower and then higher again. So it changed quite a lot. And the new dim, the red curve, so the 2016 was put on a higher tower of 7 meters, if I remember correctly, so that to make sure that it is not affected by the new airflow due to the buildings, the new buildings and the leveling of the mountain. So there are different interpretations for that, and that's where we really have to walk on eggs, as we say in French. There are 2 hypotheses. So first, of course, the numerous changes of the platform and the configuration of the seeing sensor, the DIMS, affected what they saw. And so it's just an effect of just changing the thing, this increase that we see, or indeed the local changes due to global warming circulation changed the thing, which could be also understood by the fact that, yeah, we saw that the temperature, the surface temperature is higher. So it means that there's probably more exchanges at the surface layer. And that explains why the surface layer seen by those dim monitors is changing, is increasing with time. So there is no way with such a plot that we can actually state something, which I think is very important to say, that we do have data, but it's really hard to claim something from those data. The only way would do either to do like very heavy simulations of the airflows and the change of dim locations, or to better understand the transition between the surface temperature and the turbulence. So just one thing, we know that this is only the surface layer, which is I didn't even define that, sorry, but it's the first few meters above ground. We know that because the telescopes are located, like the height of the telescope in practice, they're between 10 and 30 meters, depending on how they point in the sky. So it's 10 and 30 meters, and they are not affected by that. So the seeing that is seen really computed on the image themselves is different from the thing that is measured at the dim, which is slightly lower. So that's why we know that for sure that this is just the surface layer here that is plotted, sorry. And yeah, so one conclusion about this is really, yeah, to be careful with the data. Sometimes you can be convinced about something, but yeah, it's hard to make claims, mostly in climate sciences. So the third example, so I have 4 in total, as I said before, it's the jet stream wind speed. So the subtropical jet stream is a layer which is located at 12 kilometers altitude, plus or minus 1. It's like even more than that, so it could be a few kilometers width. And the wind speeds at this layer can go from 20 to 60 meters per second. And what you see in that video here is typically Paranal is around here. So Paranal is located by chance just where the jet stream layer is going through. And so this changes with winter and summer. So it's stronger in winter, it's the subtropical winters, and lower in summer. And so we do see that in the data. I'm going to explain why. I just wanted to say something. So this jet stream is always going from east to west, and that's exactly why the planes are going longer on one direction than in the other. It's quite important to remember that. And I think that's all I wanted to say about the jet stream. And we call it, of course, the jet stream because that's where the planes are flying, so 12 kilometers altitude. Yeah, so I wanted to say. So it actually, we see the jet stream in exoplanet imaging. So exoplanet imaging consists in reaching a contrast of 10 to the minus 6 at about 500 milliarcseconds. So I don't know if you see for those who see, but we try to look at an object which is super, super, super close to the host star. And this object is 1 million times fainter than the host star. So if we look at a host star, just any star in the sky, like there's not too far away from us, with the VLT, the Very Large Telescope, the 8-meter telescope, then that's what we see. So it doesn't look great. So this is in infrared, so 1.6 micrometers. So you need to recover the theoretical diffraction limit of the telescope. And to do so, you use an adaptive optics system. So the adaptive optics system is correcting for the atmospheric turbulence in almost real time. So the blur you see was only due to the atmospheric turbulence. But it's not enough because you can't see objects of 10 to the minus 6, of contrast of 10 to the minus 6. So you need to use what we call coronagraph, which is hiding as much as possible from the star and preserving the environment around so we can reach contrast of 10 to the minus 4. But it's still not enough. So the last ingredient is post-processing, image processing techniques. And as I said in introduction, that's exactly what I'm doing. I'm designing those post-processing, trying to understand all of the things that you have here. And with the image processing, you can reach the contrast of 10 to the minus 6 at a very small angular separation and see the exoplanets. So this is real exoplanets that are around the star HR 8799. So the critical point here is the adaptive optics. The more the adaptive optics is perfect, the more the coronagraph will be adapted, and the better is the contrast at the very end of the day. And the cool thing with this is that coronagraph makes you see some aberrations that you didn't see before. So between this image and this image, you can see all of those things, the light here that is diffracted because of some elements in your instrument or anything. So just an example, those patches here are due to the, no, I'm not gonna go into details for that. But yeah, anyway, it's very fascinating to understand every clump of light in this image. Actually, they really come physically from something in the instrument, and we can point that out. So now what? Now, when you have jet stream, you observe this thing. So this thing is called the wind-driven halo. And it's when the adaptive optics is not running fast enough. So it's not, the turbulence is varying so fast that the adaptive optics cannot catch up with it. And as I told you, it's a near real-time system, the adaptive optics. But if it's going too fast, then you have this huge spread of light. And this spread of light is really in the direction, here, the black arrow, of the wind. So the jet stream now is really going in that direction. I hope it makes sense. Does it make sense? Okay. So this affects 30 to 40% of our data, and it really provokes a loss of like 10 times in contrast. So it's really heavy. We want to get rid of that. And so we looked at the jet stream evolution with time. So we looked at 200 millibar is exactly, it's about the 12 kilometer altitude I was talking about. So that's the velocity of the wind at this. So on this blue curve here, it's the monthly mean. You can see what I told you. So it's more prominent in winter and less prominent in summer. So you see the winter, summer, and with the yearly median here in purple, you can see the typically El Nino, La Nina events, the ENSO, the El Nino Southern Oscillation. So El Nino Southern Oscillation is due to the sea surface temperature, so in the Pacific Ocean, which is varying on, as I said, 2 to 7 periods. And the warm phase is called El Nino in red here. And the cold phase of this El Nino Southern Oscillation is called La Nina. So that's the difference. So in blue, you have La Nina, in red, you have El Nino, and that's the anomaly temperature. And so we usually use this 3.4 index, which is the best suited for Parnell. And so what we can notice is that in 2015, all of our data from the high contrast instrument, so this instrument here is it's sphere in that case, is completely overwhelmed with wind-driven halo. And it's exactly the moment where we had a very strong El Nino event. So we can't really see it on the monthly mean. So we're thinking of maybe trying to see the extremes and the daily things. So it's not very visible here, but it's clearly there is something correlated to El Nino. So that's something we still have to work on. So the other thing that we saw, there is a slight increase of the wind speed of 2 to 3 meters per second, but it's very small. As you can see, there's a huge scatter of values, so we can't really state anything on it, so we have to dig deeper into that. Some papers state that, but it's very uncertain, that ENSO might be stronger, so the El Nino events might become more frequent and more violent, but stronger, but it's very, very difficult to assess anything on the ENSO, the Nino oscillation, because it's again to do with global currents, and yeah, that's something really difficult. So that's very recent papers, and there is no consensus about that. Okay, so today we don't know. So a last thing that we looked at, because it's linked with the infrared visible observations, the integrated water vapor. So as I told you, this instrument, the white box here, is a low humidity and atmospheric temperature profiling. As I told you at the beginning, Parnell is one of the driest places on Earth. So monitoring the humidity is not a fun job. It's very difficult. So if you really want to monitor the humidity in such an environment, you need those very specific devices, which are very, very sensitive to the Lab Pro. If you want to know more about it, you have the reference here. So we took the data, but unfortunately for this study, we have for now only data since 2015 at Parnell. And we see that it's getting slightly drier, but we can't say anything again because it's only 5 years, so it doesn't mean anything still. So we compared with the ERA 5 data, and we saw that it's actually consistent, even though it's not at the same altitude, but the trend is consistent. So the absolute value is not the same, obviously, but the trend is. So we plotted the trend. So in blue, the ERA 5 data I told you about, in green, the ERA 20C data, and in red, our data, which are way lower, again, with that bias of altitude. We don't see a clear trend, as you can see. And it's slightly going up since the last 5 years. But again, what does it mean? We don't know. We can't say anything with that. So that's something we have to dig deeper into it. And so we discussed with climatologists, and basically what they said is that humidity is one of the biggest chunks. So understanding the global circulation under anthropogenic global warming is the biggest chunk. So typically El Nino Southern Oscillation. And the second thing was humidity. It's very hard. So we know that globally, the humidity is going to increase, but it doesn't mean that locally at the Parnell, in the Atacama Desert, that's not going to be the case. Maybe it will be drier, maybe it won't. We really don't know. And for instance, we know that El Nino, the warm phase of ENSO, makes the altiplanico drier, or the way around, and the La Nina makes it more humid. So there's really interplays between all of those factors. So I do advise you to read the first paper by Christoph Bohm, who is really explained really well how complicated it is to monitor humidity in this area. So the conclusions of all of this pre-study that we've been doing is that we do see anthropogenic global warming in the data that we have. We see the effects, the deleterious effect of global warming. It's difficult to quantify, to claim things, as you could say. In the 3 examples, there's, it's really hard to say, okay, this is it. But it's very important to understand better from large to small scale the processes that are playing. So probably astronomers can help because we do data, and in our data we do have like a lot of information. So for instance, turbulence or monitoring. I just wanted to point out the very recent Nature Astronomy special issue on climate change. So you have the free links on the Astronomer for Planet Earth website, I think. So the whole, like there are 6 papers in an editorial, and they're really summarizing many things. So go ahead. And the very last point, so the perspectives, of course. So we want to extend this study to study more parameters that at parallel, but also compare with more models, more measurements, more predictions. Maybe study other man-made alterations like aerosols. You know that Chile is a place where they have a lot of mining industry, which produces lots of aerosols in the atmosphere. Light pollution as well is a big issue, and same for the mining industry because mines, they were just working 24 hours a day. It's also possible to investigate other observatories because Mauna Kea Observatory has very, very different setup compared to Chile. And one thing would be great to have like a global database for astronomers to gather all of this knowledge. So thank you very much for your patience with those things, and don't hesitate to write me.
Fantastic. Well, thank you so much for that talk. That was really interesting.
We hope you've enjoyed today's talk. Each of our talks is followed with a Q&A session that you can learn more about in the video description. If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.